Hello, class. This is lab number 7, I believe it is, and the last lab, it's the flexure lab, shear force and bending moment diagram lab. And what I wanted to do was to take you to another site. Let me bring that up here and share it with you. Just a second. There it is. As you can see from what you're seeing on Zoom, the website is called SkySieve. I hope I'm pronouncing that right. And the web address is https://skisieve.com/free-beam-calculator/. Now, and you can see that right up here. I'll actually highlight it there for a second. I think that you can see that. So that's the site that I'd like you to go to. And when you do, I'm not going to send this to you in email. No, you're going to write it down. And when you go there, you're going to see this. You're going to see something that shows you that you can add a beam, add supports, add point loads. And here's what I want you to do. I want you to go here and I want you to create a simple beam. So you're going to add a beam. It's going to ask you for the length of the beam, and I want that beam to be 50 meters. Now, 50 meters is approximately the distance of an overpass segment. A rather long 150-foot overpass segment in between different columns that are supporting that overpass segment on a highway. So let's add that beam. There you go. Now, for a beam like that, on one end, you're going to have a pin support, and on the other end, you're going to have a roller support. So the pin support, we're going to put 0 meters from the left end, right? So you can see I've added that. And then we want to add another support, but this support we want to be a roller support. And we're going to add that 0 meters, but from the right end, and add that, and you'll see it changed at the last second there and went to 50 meters, but you get the general idea. It references everything to the left end. Now, I want you to put a couple distributed, or actually a couple distributed and 1-point load on there. So for the distributed loads, I want the distributed loads to start at 0 meters and end at 25 meters. So starts at 0 meters and it ends at 25 meters. And I want it to begin with 200 kilonewtons per meter loading and end with 40 kilonewtons per meter loading. Does everyone see that, how I've got it on the screen? So I'm going to add that distribution. And now what I want to do is I want to add a symmetrical distribution to that at the other end, of the beam. So we're going to add another distributed load, except this time we're going to our start point is going to be at 25 and our finish point is going to be at 50. And we're going to start at 40 kilonewtons and we're going to end at 200 kilonewtons. And that's what you're going to get. Does everyone see how that's been laid out now? That sort of replicates the load of the concrete and structure across a support like that. So there we go. We've got that. Now, what I want you to do is I want you to add a point load to reflect the moving traffic, the maximum. If there was a traffic jam on that overpass, what would be the weight of the cars on that? Let's say every car is about 3 meters long, right? So, in fact, why don't we say every car is 5 meters long? Just to give ourselves, well, no, that would actually change it the other way, wouldn't it? Anyway. Okay, anyway, just to make it simple, I'll say that every car is 5 meters long, and including the space in between cars, even when they're in a traffic jam. So if it's 5 meters, then we're going to have 10. And if we've got 4 lanes of traffic, then we're going to have 40 cars on that bridge at one time. Now, 40 cars, how much does a car weigh? Well, I think everybody knows that the mass of a car is about 2,000 pounds, right? Maybe we should double that and use a safety factor of 2 and say that they're 4,000 pounds, because, you know, there could be trucks, there could be cars. Trucks are heavier than cars. So we go with an average of 4,000 pounds. So if it's 4,000 pounds, how many newtons would that be? Well, it's about 4.45 newtons to a pound. So that would be about 20,000 newtons, give or take. So 20,000 newtons per car, and 40 cars on the bridge. Why don't we say 50 cars on the bridge? So 50 cars times 20,000 newtons is 1 million newtons, isn't it? I'm going to say that we've got about 800,000 newtons on there. So let's add a point load. Let's say all those cars happen to be in a traffic jam, but then they're all piled up in the middle of the bridge. So I'm going to put 25, you know, worst case scenario, at 25 meters, we're going to have a point load of 800 kilonewtons. So let's add that to the distribution. So that's what we've got. Now go to solve. And what this does is it solves, of course, for the supports. You can see that the supports on both ends are going to be 3,400 kilonewtons. It's a simply supported beam with pretty much symmetrical forces. If I go down, you can see what the shear force diagram looks like. And I think everybody can see that shear force diagram. Oh my God, that's not a linear distribution, is it? Right? It's not a linear graph between those 2 points like it is up here. No, instead, it would be a polynomial of degree 2, polynomial of degree 2, right in this area here. I think everybody can see the area that I'm highlighting. And I'm sure that you could figure out from the distribution above what the equation is for that parabola. I hope you can anyway, because that's part of your lab. Part of your lab is, I want you to figure out at 12 meters from the left end. Write this down, everybody. 12 meters from the left end, what is the shear force? What is the shear force 12 meters from the left end? And I know what you're thinking. Oh my God, this is going to be a cubic down here, because I'm taking the integral of a second-degree polynomial, so it's got to be a third-degree polynomial for this down here. That's right. And I want you to find the bending moment 12 meters from the left end. Now you're probably thinking, oh, hey, what Professor Grunquist doesn't know is it says the bending moment at X meters along the beam is, and no position entered. I'll just enter 12. Oh my God, there's an alert. You have to actually pay for that. So no, you won't be doing that. You will be figuring it out yourself, but you're going to use all these numbers. You have the maximum number here. I think everybody can see that, right? And you also have the various numbers here. So you should be able to easily figure out, using your shear force and bending moment knowledge, what is going to be the shear force 12 meters from the left end, right about here, or maybe here, and what is going to be the bending moment 12 meters from the left end. That's it. That's the whole lab. And really what it is understanding how to figure out from linear equations or linear distributions, and then finding out exactly what that equation is. That's the key, isn't it? Once you find out what the equation is for this distribution right here, right? And how it plays into this right here. Once you figure out what that equation is, then it's easy to do the next equation too and find the area under the curve. That's what I want you to really do here, is to understand, not mathematically, but graphically and diagrammatically, what is the integral of an equation. Okay, that's it. Thank you very much. Get those done. It's your last lab. Get it into me. See you later. Let's see. I'm going to stop sharing. There I am. And I will let you go. That is lab 7 and the last lab. Get that done and into me, and you're all done with labs.